welcome. So today's second speaker of the day is Tom Berger, who graduated from UC Berkeley in the late 20th century, he says, and then got his PhD in astrophysics with Phil Scherer and Alan Teitel at Stanford, before spending 17 years at Lockheed Martin, where he was the lead for the ground-based observing program, working with the Swedish Solar Telescope, and also the development of optical and near-UV polarimetric systems for instruments on Hinode SOT and the Slitjaw system on IRIS. So following Lockheed, he was 2 years as a project scientist for DKIST at NSO, and then 3 years as the director of SWPSE here in Boulder, before moving to CU Boulder to help start the Space Weather Technology Research and Education Center, Space Weather TREC, with Jeff Thayer and Dan Baker. And he's currently the executive director of TREC and the head of the Deep Learning Lab for solar and space physics applications of machine learning. But today he's talking about SPOC. Thank you. If you've got that, I'll just
turn this on again. There we go. Yeah, thank you very much for inviting me today to give this talk. I'm not going to talk about TREC or the progress we're making there or the Deep Learning Lab. That's a whole other seminar I'd be happy to give some other time. This time I thought I'd talk about a mission that we've been developing with LASP and Lockheed, and also Naval Research Laboratory support, and also Ball Aerospace Corporation support, that I presented at the L5 meeting at Stanford a couple of weeks ago as well. So this is kind of a redux of that talk, a little bit longer, a little bit more in depth. And the idea is to address a shortcoming that we all know well, and I'd learned quite well when I was director of SWPSE, and looking at all the really atrocious solar wind forecasts that come in, and all the CME errors that we made, and realizing that probably the largest single contributor to that was getting the solar wind wrong, because we were getting the polar fields and really the overall spherical magnetic field of the sun wrong, but in particular the polar fields. And so this got my interest up in thinking about how could we really measure these fields in not only a research way, but also in a way that gives us a continuous operational basis for not only learning about the poles, but having an operational input to forecasting and improving the forecasting. So what I'll do is go through some of the motivations, and this is again the main one. What you come to realize when you work with magnetograms of the sun is quite rapidly is they really only cover about a 60-degree angular coverage of the disk. And so any given magnetogram will necessarily not reach the poles. Signal to noise up there is too low. And in addition, you'll also miss out on active regions coming around the limb. And so this is just a reality of the signal to noise limitations of these instruments, and also looking at an atmosphere at an angle. Once you get up to these very high lines of sight, the penetration length through the atmosphere just destroys all of your resolution. And of course, we know that what people like to do, however, is make these infamous synoptic magnetograms, which purport to sort of give you the entire sphere of the sun in magnetic field. What you'll notice here is that these maps typically go all the way to the poles, in other words, 90 degrees north and south. Now, how do they do that if the magnetograms don't reach that far? They do that by extrapolation. And so really, when you see these things, the areas at the poles, in particular, these banded areas I've just highlighted, are just best guesses, extrapolations from existing data, depending on how they made the synoptic magnetogram. Another way to see this is if you take a raw set of magnetograms and make a long-term synoptic like this. This was done by Cooper Downs with HMI data over the entire HMI mission to date. You can clearly see the oscillation of the polar fields as the Earth goes around its ecliptic 7-degree inclined orbit. You alternately see the north and south pole of the sun a little bit. And so that's truly a synoptic magnetogram. That's what they really should look like. But we, of course, need them to model the entire global field of the sun. And so people often do this. They take a synoptic magnetogram, they wrap it around the sphere, and they say, there we go, there's the entire magnetic field of the sun, and now let's go ahead and model the corona. But we all know that not only is that invalid because of the polar fields, but the synoptic map is made over the course of 25 days. So this is really an amalgam of 25 days of data, none of which is exactly current, except perhaps one small strip corresponding to the current time. So this is really not a valid way to be constructing a global field of the sun. But it's the best we can do, right? That's all we can do from the ecliptic sun-Earth line standpoint that we're limited to right now. We can get glimpses of the polar fields, and we've done that with Hinode. This is data from the SOT magnetogram instrument that I worked on when I was at Lockheed. This is taken in September, so we're looking at the North Pole here. And you can see we can get a glimpse of the pole, and all the way up to the pole. One of the really, I think, breakthrough discoveries of the Hinode mission was that there are very concentrated kilogauss magnetic concentrations in these far polar regions. That was not expected. It was expected that the field up there, by the time it got up there, carried by the meridional flow and subject to the diffusion that we thought was going to be dominant, would simply be sort of a background, low field, background scattered effect. And it's really not. There are these very concentrated elements up there. We still don't know the cause of these elements or what's really behind these pretty large scale, larger than granular scale concentrations that Hinode has seen. That was the original one that created the Tsuneta paper in 2008. But since then, Shiota et al. Have taken this and done it as a sort of a synoptic program. And here you see two polar fields from, I guess it's 2008, and then again in 2011 later in the cycle. And you can see there's definitive changes in the structure sizes here. And again, we don't always observe these polar regions, of course, as I said earlier, and we don't always do these scans with SOT. So it's not really clear what the dynamics of these fields are, either in short-term or long-term effects. But it is intriguing that there's more up there than I think we thought there would be. You can also compare chromospheric magnetograms to photospheric magnetograms at the poles. So this is showing SOT data on the left, where you have the iron 6302 photospheric magnetogram shown earlier, but in this format, looking at it as a disk. And then you see below it that's the, I can't read it actually, the 5896, yeah, that's the sodium line chromospheric magnetogram. And you can see there that here we have this sort of spreading of the field into the canopy field. So you have this distinctive sort of black-white canopy signal in the chromospheric magnetograms, also seen in the Solis magnetograms in the same lines. And so the polar fields are doing what you would expect from highly concentrated photospheric magnetic fields. It's just surprising to see them doing that at these very, very high latitudes to some degrees. Yeah, I mean, it's not completely unexpected, but I think it's funny that the size of these structures is somewhat larger than we thought, given the diffusion that we thought would dominate up there. You don't find it?
It would surprise people to subscribe to an overly wrong picture of the solar map.
Well, there are those people. They do exist. I won't tell you if I'm one or not, but I will tell you that I was surprised by those images, not so much because of my dynamo model beliefs, but just because of the clarity and the size of the structures that did result. But this just goes to show, really, the point of these slides is there are things up there that we need to investigate further. We'd like to see the dynamics of them. We'd like to see the flow fields that they're being subject to. Those are not possible to capture with the Hinode instruments. So we really just have glimpsed what's possible up there. This is a slide from Cooper Downs that he showed at the L5 meeting at Stanford a couple weeks ago, which highlights what the coronal modelers are doing with our data. So again, you see on the far left here the infamous synoptic magnetogram, in this case with very much boosted polar fields. This is using the Gong magnetogram, but with the ADAPT model of flux transport, which is used to sort of artificially transport flux to the poles and fill in what they are now thinking should be at the poles. So that the two inputs that Cooper is showing here are the Gong magnetogram, a full sphere, quote unquote, magnetogram, and then the coronal heating model on the right. And those two inputs result in a lot of different products for coronal modelers, one being the 3D magnetic field you see in the lower left, the electron density white light, sort of artificial eclipse images they produce for eclipse predictions, the solar wind model on the far right, and also the EUV heating, the simulated AIA models, all go back to this one basic input of a global photospheric magnetic field based on line of sight magnetic field measured on the Sun-Earth line. And what Cooper has shown is that the ignorance of the poles has led to some pretty obvious difficulties. And here what he's done is shown the observations from AIA on the top row, his baseline simulation of AIA output in 173 and 191, 171 and 193, and then on the far right column, the EUV heating, essentially a temperature map. And if he artificially boosts the polar field by 50% within 30 degrees of the pole, the heating of the corona changes dramatically, not just the structure, but the heating as well. And that was a surprise to, I think, all of us. On the right here, he's showing these simulated eclipses that were done for the July eclipse, but were done ahead of time, starting in May and June, to anticipate what the July eclipse would look like. And you can see that the boosted polar flux changes the streamer structure quite dramatically. But again, it also it changes the emission as well, and that was somewhat unexpected, but it's just a good illustration of the fact that when you get the poles wrong, you get all kinds of things wrong. This is another example of the open flux problem, as we call it. This is a long-standing problem in which if you add up what is apparently the open flux, open magnetic flux into the heliosphere based on any synoptic global map, in this case the HMI line of sight maps, and you put your favorite coronal model on top of it, the flux that you anticipate at 1 AU is somewhere between 40 to 65 or 70% of what's actually measured in the solar wind, as shown here. So this is HMI line of sight with a potential field source surface model, sort of your standard 2.5 RS source surface model, and it produces about 65% of the open flux that's measured at the L1 point. Similarly, if you then say, well, let's just use the HMI line of sight magnetogram, identify the open field, and sum up all of that flux as shown in this diagram on the left, that gets you to about 71% of the open flux field measured at 1 AU. So there's still a problem with missing flux there. Any of the, and this isn't just an HMI problem or a PFSS problem, any of the magnetograms, any of the models you use will come out with about half of what you would measure at L1 for reasons that aren't quite fully understood. One of the reasons could be that the magnetograms themselves are not calibrated. They're because we don't have an absolute standard to look at the sun. We don't really know exactly what a magnetogram signal should be from a remote observing standpoint. So we have a project right now with NSO to go ahead and try and calibrate using models and convection models, the gong magnetogram. And we've gone through that exercise and produced a recalibrated gong, if you will, which does boost the flux over the disk. It boosts it pretty much all over the disk by varying degrees. And we were hoping that that would account for a lot of this missing flux problem when we reran the open flux problem. However, it's really only accounting for about 35 to 40% of the discrepancy at this point. So there's still missing pieces to this open flux problem, and we think that the polar fields are probably what are causing it again. If you get the polar fields wrong, as shown earlier, you can get the entire heliospheric current sheet wrong, and therefore the flux at any point in the heliosphere could be off. So this is a good example again of where the polar fields might be showing their hand here and what they're doing. On the right, I'm showing another study by Meng Jin at LM Sal, in which he took the flux from various magnetograms and boosted them until he boosted the polar flux until he got the correct 1 AU flux, and you can see it's a factor about between 2 and 2.5 that he had to artificially increase the polar flux in order to match the 1 AU open flux. And so a lot of the modelers you talk to will now just artificially boost magnetogram signals by some factor, arbitrary factor often, in order to say, well, I know that it's low, so I'm just going to multiply it by a factor before I run my solar wind model. In this case, this would argue for a factor of something like 2 to 2.5 on these HMI magnetograms. But I know from going to CCMC and talking to them about when they run the WSA Enlil solar wind model, the inputs to those are the gong synoptic maps. They multiply them by a factor of 4 before they put them into the solar wind model. And I said, factor of 4, why factor of 4? And they just like, well, it seems to work best. And That's huge. I mean, that's a gigantic change in the overall flux of the magnetogram, but they're like, yeah, it works better, so we do it. It's a knob they turn, and they've actually just set it at 4 for now. So with the recalibration of Gong, maybe that goes to 3, something like that, but a lot of work to be done in this area still. Another obvious place that we need to do polar work is for the polar helioseismology gaps that we currently have. This is showing the internal rotation map, Michael Thompson map, which for years has had this blank at the poles. We all know that we've never been able to really see what's going on at the poles. Similarly, there's very interesting potential convection zone effects with jets and other things, which we can't really resolve beyond about 60 degrees to 65 degrees from the equator. And so looking at these meridional flows, these internal flows and the rotation, the convection zone structure, and possibly the magnetic field origins is going to be very interesting from a polar standpoint if we could get up to see a polar standpoint. And that's one of the biggest challenges in thinking about getting data that's at the true pole. Magnetic fields, you can think of a flyby and getting a pretty good idea of what's going on up there with a flyby of a magnetograph. But for helioseismology, all of those observations depend on beating down the noise over a long period of time, typically weeks to months. So you need a long period of time at which you're above a certain latitude to really get into the higher signal to noise helioseismology. So this to me is one of the biggest drivers of why we want to take a polar mission and get it to a point where it can actually stay above a certain latitude for a given amount of time and repeat that measurement over and over again. It argues against a flyby for this kind of science. Also, what we'd like to look into is some of the polar surface flows, which again takes a fairly long integration time and ideally a repeat time in which you can sort of really revisit these areas over and over again. This is looking at the North Pole of Saturn, of course, with the famous hexagonal jet stream structure, which I don't know that they've really explained this structure in detail yet, but it's a fascinating view of what a gaseous spinning body can do under some dynamics. And then, of course, the South Pole of Jupiter from the Juno mission is shown on the right there. And I don't think anybody expected to see that much vortex structure at a pole of a gas planet until Juno went over. And the fascinating thing is Cassini said, back in 2000, when they did their Jupiter gravitational assist out to Saturn, they got, I think, 10 or 15 degrees below the equator, and they glimpsed the pole of Jupiter, and that's what they saw. And a lot of people had thought, well, we've seen the pole of Jupiter, right? But if you now look at the Juno data, that's an overlay of what we see at the same pole from Juno. So this just goes to show that getting 15 degrees, 20 degrees out of the ecliptic still doesn't get you enough direct line of sight down onto the pole to resolve the kind of structures that may be there in the sun. We don't know, but we certainly can't, I think, say that just because we've glimpsed the pole from 7 degrees in the ecliptic that we can say we've seen what's to be seen there. That is the North Pole of the planet Jupiter. Oh, actually it's a full color CCD image. There's a 3-color CCD on Juno, but it's been a little bit boosted with Photoshop and things. There's a whole online community that takes the Juno data and does all kinds of stuff with it. And there's a couple of people who do, I think, the best job at sharpening and color boosting. So Jupiter likely doesn't look that blue in reality, but the structures are real. There's no playing with the actual structure there. It's just a way.
So it's obviously it must be luminosity, but is there an interpretation of what we're seeing physically?
Yeah, I mean we're seeing the upper atmosphere of Jupiter, and so you're seeing the flow fields in the upper atmosphere of Jupiter around its north pole. And the surprising thing again is the number and the intensity of the vortex structures there, which I don't think was expected by anybody. And it's up for debate as to whether the sun, being a much more energetic convective structure, would have similar structures, but I don't think we can rule it out. I think there's a chance that even in the convective structure of the sun and in the high temperature envelope of the convection zone, there could be systematic flows up there that are as interesting as these large-scale vortex flows we see in a gas giant. So that's that's kind of the motivation of showing this picture. And then finally, as I mentioned, the accurate solar wind forecasts are really something that need to be investigated. This is a particular case that I was involved in when I was at SWPC, which was a blown forecast. It was a high-speed stream coming from a coronal hole, but we thought the coronal hole was not going to be effective at Earth. And so the forecast, as you see on this diagram here, which is actually Nick Argy's kinetic code, but the WSA INLA was giving the same thing, was forecasting very low wind speed. In fact, the observations were, the high-speed stream came in at about 700 kilometers per second, and a G3 storm was the result. Not long, but it was a G3 level for at least 3 hours. And the forecast was essentially for a G1 or less. And so that was pretty bad, but not a typical example of a forecast that missed the high-speed stream because of the underlying magnetogram leading to an inaccurate solar wind approximation. So we went back and reforecasted this. That's just outlining the peak that we missed. We reforecasted this using ADAPT. And again, ADAPT is a flux transport model which boosts the polar field by cranking up the meridional flow, for one. And it also does some things on the unseen side of the sun to approximate better, apparently, the overall field of the sun. And lo and behold, boosting the polar field changed the heliospheric current sheets sufficiently to connect the coronal hole and grab the high-speed stream. So the main thing there, though, again, that ADAPT ended up doing was boosting the polar fields by a good amount. I'm not sure exactly how much in this case, but you can kind of see that over here. I highlight that there with the ellipse. There's a lot more field in the South Pole than there was in the original Gong magnetogram. So that's a very good illustration of what you get when you play with the poles in your solar wind model. And then also, the solar wind is sort of the background flow on which CMEs transit throughout the heliosphere. Of course, we know the very large ones don't really care about the solar wind, but some of the smaller ones certainly do. And another reason you want to get out of the poles is not only to get your solar wind model right, but just to see these things that are coming directly towards the Earth. So here's an example of what we call a halo CME, which is a CME essentially coming directly towards the Earth or close to, directly towards us from the Earth's vantage point. These are LASCO CME coronagraph images. You really just see a ring around the sun. And the diagram on the right is showing that this could be two things. It could be a very wide, slow CME, or it could be a very narrow and fast CME. They both give the same signal on the two-dimensional projection on the sky. And so you don't really know from this vantage point how fast the CME is going. And unless you have stereo working for you to show you a side view, which we do now but will not in the future, probably very near future, you can't really predict the arrival time of this structure. However, if you had a polar vantage point, if you had something out of the ecliptic looking down, that CME would turn into a traditional CME that you could then calculate the speed of and get an accurate arrival time forecast on, hopefully. It will die. We will all perish eventually, and I think stereo will hopefully predate all of us. It's been out there a long time, and it's not clear how long it's going to last. But we can't count on it being there throughout the next solar cycle. I think it would be surprising if it lasted that long, unfortunately. I like being surprised, though, so I'll take it. If it lasts through the next solar cycle, that's great. But the other thing about stereo is it is drifting in location, so it's going to become less and less effective as a side view as it drifts closer and closer to the Sun-Earth line over the next 5 years or so. So ideally, we'd like to get something out of the ecliptic and look down. So, it's not like we've never been out of the ecliptic before, right? There have been past missions that have done this. The Ulysses mission is the famous example, launched in 1990, I believe. Unfortunately, the in situ sampling mission was the only one launched. The US imaging mission was canceled. But we do have this example of how to get to Jupiter, how to get out of the ecliptic, and how to make measurements of the solar polar regions. Now, they only got to 70 degrees, or 80 degrees. I can't remember exactly. They didn't go directly over the pole, and they stayed in the JGA orbit. In other words, they were essentially orbiting Jupiter and the sun. So they had a return time of sort of 6 years to the poles. But they did fantastic science on the solar wind. This is, of course, the iconic plot of the solar wind over the course of the solar cycle 23, which really was an eye-opener for a lot of people in terms of the latitudinal structure of the solar wind. So it did a lot of good science, but unfortunately it could not look down and make any of the measurements that we talked about earlier. Another one that's going to have a glimpse of the pole upcoming is Solar Orbiter. That's shown here. Now, they're not planning on getting to a very high latitude until their extended mission, at which point they hope to be at 33 degrees. They will stay in a pretty elliptical orbit, which complicates your helioseismology somewhat. But they will get 10 days per orbit of looking at the pole. And this on the right is showing an ecliptic view of a synoptic map, sort of famously wrapped around the sphere, of course. But on the right showing, yes, even at 35 degrees, you do get a significant view of the poles. So I think Solar Orbiter can be counted on to give us our first glimpses of some real structure at the poles. But again, it's going to be just glimpses. It's 10 days per orbit. There's a telemetry restriction that will make it difficult for them to really do any long-term helioseismology or flow tracking. But I think they're going to be successful in showing us what we could actually explore further. Yeah. This, I think it's pretty fast. It's solar. It's Parker light because it's 0.35 to 0.8. So it's, what is that, like 6 months? Or, yeah. Yeah. There's also been studies for a while now because people have realized that the poles are important for a while, and there's been various technologies and designs applied to the problem. Solar sail missions have been studied by at least two groups, one at ESA by Porcio et al., and then one at NASA. Paulette Luer has looked at using solar sails to get out of the ecliptic. And that top diagram, I don't know if it's totally legible, but basically the problem with the solar sail is you end up taking 6 or 7 years just to get to the inclination shown here, which I believe is 60 degrees. So it's 6 to 7 years to get 60 degrees out of the ecliptic. It gets there, but it's quite slow. So people have looked at other solutions, for instance, using not only a Jupiter gravitational assist, but an Earth or Venus gravitational assist on the other side of the Jupiter's slingshot to circularize or roughly circularize, or not circularize, but lower the eccentricity is really how to say it, the orbit, perhaps using ion engines as well. There's the SPORT mission out of the Chinese Academy of Sciences. And then Jeff Newmark at NASA has put forward the SolPEX mission, which is a single ion engine relying on a Jupiter-Venus resonance to try and get you out of that slingshot orbit that Ulysses was in and get more frequent data. And that's shown below in the diagrams where you can see this encounter with Venus over time, sort of leading to a less eccentric orbit. And then finally, we have the Solaris mission, which Don Hassler et al. At SWRI have put in as a mid-X mission in the recent round of mid-X proposals. This again is, I don't believe it's an ion engine spacecraft, but it is relying on the JGA and VGA resonance to try and get you out of the Jupiter orbit. And I don't know how often those launch opportunities come up, given that you have to have that strict alignment of Venus and Jupiter. But it is an intriguing mission. I think that's kind of a pathfinder that we should look to see if we can really see what's at the poles quickly in a relatively cheap mission, and therefore use that as a strong argument to go ahead and do a much more ambitious mission, which I will now describe. This is the mission that we've come up with, which the basic philosophy behind the Solar Polar Observing Constellation, or SPOC, is that we want to have something out there over the poles in a very high inclination, in a very low eccentricity, Earth-like orbit, so we can do the helioseismology, and we want to have two of them out there. One reason to have two is to view both poles simultaneously, so you don't have to wait for sort of 180 days to see the next pole. And two, because they are therefore operational. You've got a backup essentially. You've also got a continuous data source. When one is blacked out by, for whatever reason from communications, the other one will presumably not be. So you've got a very robust system out there, and you can do both the exploration mission that we've talked about, looking at the polar convective flows, doing long-term helioseismology. You can also, however, do a 7-year operational mission in which you've got a coronagraph looking out of the ecliptic at CMEs. You've got the better solar wind modeling, et cetera. So the vision here is to have sort of a hybrid research and operations mission, like SOHO, if you will. SOHO was a strict research mission, but very quickly the operations community jumped on board and said, this is great. This is what we've been wanting for a long time. We can use these data right now in space weather forecasting. So this would be essentially a SOHO out of the ecliptic, doubled, so that you get the operational robustness. And as I said, we're looking for a high inclination orbit, and so we want to get there quickly as well. So really, your only option is a Jupiter gravitational assist. You've got to use Jupiter. You've got to get out there. Then we'd like to get to that low eccentricity. As I said, we have 2 spacecraft for operational redundancy. The low eccentricity means that you're going to be carrying ion engines and trying to use those to circularize or roughly circularize your orbit. Because you're going to Jupiter, because these spacecraft have a lot of fuel on board, they're large, you need a large rocket and you have to limit your payload mass quite a bit. And so we struggled a lot with what instrumentation to include. In the end, we ended up with relatively limited measurements compared to some of the L5 missions you might have seen, where it's just kitchen sink, essentially SOHO plus out to L5, where you don't have to have as much launcher C3 to get out there. This, because of the demands to get out to Jupiter and out of the ecliptic, we really can only carry, we think, 2 large imagers, or they're actually relatively compact imagers. One, a vector magnetic field measurement instrument, which is, as I'll show, the Lockheed compact magnetograph instrument, and another, the compact coronagraph instrument from NRL. And then, of course, in situ instruments, they're light, they're cheap, they're relatively cheap anyway. They're relatively easy to carry on the mission. So that's sort of the vision of the mission, the outline of the mission. The design assumptions that are going into this, again, it's a constellation of at least 2 spacecraft in phased orbits around the sun. The orbital requirements, again, are we'd like to get inside 1 AU in a high inclination orbit with a low eccentricity. Therefore, again, we're going to use the gravitational assist of Jupiter. However, you still need a specific energy of about 135 kilometers squared per second squared, which is very large. As a comparison, it's not the largest that's been seen. As a comparison, Parker Solar Probe is 155 kilometers squared per second squared. One of the reasons they had to have a very light spacecraft, and then they had to use a Delta IV Heavy. However, these spacecraft can't be that light. We're looking at sort of hopefully something less than 700 kilograms dry mass and 300 kilograms of fuel for the ion engines. The solar electric propulsion that we're baselining are the ZIPS engines with the number shown there. Of course, very low thrust, very high ISP, and requiring about 13 kilowatts of power to run the engines during the periods. Now, there's 2 candidate launch vehicles that can do this right now. One is the Falcon Heavy, shown on the left there, which in nominal configuration can get 64 tons of orbit to LEO, but can only get about 900 kilograms out to Jupiter. So that gives you an idea of how difficult it is to get out to Jupiter, get out of the gravity well, get out to Jupiter with sufficient velocity to do your slingshot maneuver. And so we're just barely able to put 1 spacecraft on a Falcon Heavy with sufficient secondary boosters and things. However, there's also the SLS coming up, and that shows you the scale. There's a roughly to scale. The SLS is a much larger rocket. It can take 105 tons to LEO. It can take about 2,000 kilograms, as I'll show, to Jupiter. So we could potentially put both on an SLS. We're looking at that option now, as I'll talk about later. A little bit on the instruments. This is the CMI instrument of Lockheed Martin. It's essentially HMI shrunk by a factor of 2. So it's shrunk by a factor of 2 in all directions, except it is 1/3 the mass. So it's quite low mass, 33 kilograms as opposed to 90 kilograms. We would fly a 2K by 2K detector, just again shrinking everything by half. But this is essentially a design that I think is quite mature based on the HMI heritage. And so we're more comfortable going with this than some of the other compact magnetograph instruments that are out there now, which are just now being sort of spaceized, if you will, and brought to TRL 6 or 7. The C-Core, as I mentioned, is a instrument from NRL. That will be flying on the Space Weather Follow-On instrument to L1, hopefully, and on the GOES-U platform. The plan is currently to put it both on GOES-U and out to L1. So this is, again, a very highly developed design. It's essentially a LASCO heritage instrument, but it's very much smaller, 15 kilograms total mass, 11 watts power. It's a really fascinating development from the LASCO instrument. And then looking at the in situ instruments, these are just some samples that we could potentially choose from. These are essentially, on the two on the left there are essentially SWRI instruments that have been used on the Rosetta mission or about to fly on IMAP. The beauty of, for instance, the IMAP CODICE is it's a full 360-degree measurement of energetic ions and solar wind. You don't need to spin the spacecraft to get your measurement of the full pitch angle distribution. And of course, we don't have a spinning spacecraft, so that's ideal there. But again, these are all pretty low weight and low power. And then, of course, the flux gate magnetometer and the search coil magnetometer would be relatively easy to carry on these spacecraft. So that's sort of the instrument complement we're looking at. The spacecraft itself is being designed at Ball, and this is sort of the rough outline of what they're looking at now. It's essentially a large box to carry the fuel for the ion instruments and the large antenna that you need for the Ka band communications, and then the very large solar panels you need to power the ion engine. So it's essentially just an ion engine spacecraft with, as you may not even be able to see them here, the instruments are all just tucked right in there on the solar array yoke, much like the GOES instruments are on the GOES satellite. So the instruments are compact and small by design, but they're small enough that they fit onto the yoke, and so you can hardly see them on this diagram. So that's kind of what we're looking at. Again, about a 700 kilogram dry mass. This is, of course, the requisite diagram of, yes, it fits in the fairing. This is a Falcon Heavy 4-meter fairing. It fits pretty comfortably in the Falcon Heavy 4-meter fairing. This is a close-up again of the spacecraft. Right now, the ZIPS thrusters are put on the edges of the spacecraft bus. That's probably not optimal, because if you did have a failure of one and you didn't catch it in time, you'd get some asymmetric thrust. It's a low thrust, but if you didn't catch it in time, it might actually start spinning your spacecraft. So we're looking at collecting those closer together right now. But for right now, that shows you sort of the distribution. Again, the solar panel yoke with all the instrumentation tucked nicely in there. This is also not showing the in situ instruments, which would probably be scattered around the edges of the bus, not on the yoke necessarily. This is the 25 centimeter Xeon ion propulsion system, or the ZIPS 25 system. The reason we chose this system is it's already been used quite a bit on the Boeing Geosync satellites to get from geotransfer orbit out to Geosync. So there's a total of 10 years of operational data. There's 68 of these in orbit right now on 17 different spacecraft with at least 2 each. They've had 16,000 hours of total flight time. So these are really well tested. These are battle tested and ready to go. There's other ones that have higher thrust or sometimes higher impulse, but I don't think any of them have this kind of heritage. So this is, right now at least, the best shot that we can see for ion engines. Now, how do you get to this exact orbit using this spacecraft? For this purpose, we've worked with Natasha Bosanic, a professor of astrodynamics at CU, and her graduate student, Thomas Smith. And they went through, given these parameters shown here, the assumptions on the spacecraft, mass, and the thruster capabilities, and looking at different launch vehicles. They've gone through and really done a detailed orbital analysis and shown that it is possible to get even these large spacecraft out there. So the first thing they did was what's called a pork chop plot, which shows how do you get to Jupiter, what does it take to get to Jupiter, and it's a little hard to see, but we're down in each of these sort of large slanted vertical lines are the Jupiter encounters that you can achieve it from Earth. And so in this box here, we are achieving relative velocities to Jupiter, which allow the inclination maneuver. Those all concentrate in the C3 regime of between 130 and 140, which is, again, challenging, but it's possible. And so what you end up with, if you achieve that C3 of about 130 kilometers squared per second, is an orbit which takes you to Jupiter, gets you out of the ecliptic. And then the idea that essentially has been analyzed by Thomas in detail and was published in that paper I showed earlier is that you begin perigee firing the ion engines on the first orbit. And they are essentially impulsive enough that within 3 orbits, you're essentially at your operational orbit. So this is a rapid achievement of the operational low eccentricity orbit. This shows, the plot on the left shows sort of a timeline versus solar latitude. You can see that you're over the pole of the sun the first time 2.7 years after the Jupiter gravitational assist. So roughly 4 years after launch, you're flying over the pole of the sun. And then you're circularizing down to that flat oval at the bottom, within about 5.5 years, you've achieved the low eccentricity orbit at 88 degrees out of the ecliptic. The plot on the right is just showing you the firing passes in red, and then the solar latitude oscillating and settling down relatively quickly to that final operational orbit. So the parameters that it ends up with are, if we were to get a launch September 28th, 2025, say, within 15 months we're at Jupiter, and within about 5.5 years we're at the operational orbit at 88 degrees out of the ecliptic. The propellant required for this is only 250 kilograms, so we've got about 12% reserve on board, which is a good thing to have. And again, the eccentricity is about 4%, so Earth-like, and the orbital period is about 300 days. It's inside, it's at about 0.8 or 0.9 AU. So another example of the advantage of this is that when you are out of the polar regions and you're coming down into the ecliptic, there will be times when you're roughly in line with the Earth's orbit, but you are at 0.9 AU instead of 1 AU, and any CMEs that go by are going to hit you long before they get to even L1. So this could be an early CME warning platform when it's in the right orbital configuration, which won't be, it's not designed to do that, but there will be times when this orbit will be essentially a CME warning orbit, which is a nice plus. This is the requisite table showing the time above a certain latitude. You can see for the 3 different orbits, you have different times above a given latitude on the sun. The operational orbit on the bottom is the most interesting, of course, and you can see that you get above 55 degrees about 55 days per orbit, going down to, of course, as you're zipping over the pole, only about 2 days between 85 and plus 85 and 90 and minus 85, if you will. But still, that's just because you're going straight over the pole, essentially. So this is, again, the orbit that will enable long-term helioseismology of the poles, because this is the orbit you stay in. You don't actually change out of this orbit until the spacecraft runs out of fuel or something else happens. Now, how do you get 2 spacecraft? Say we were to launch the 2 spacecraft on one rocket. They're both going out to Jupiter together. How do you get them to be over different poles at the same time? How do you phase that orbit by 180 degrees? Well, it turns out that Thomas came up with a pretty clever way of doing it, which is just to wait on the thruster firings of one relative to the other. And so what I'm showing here is the flight out to Jupiter, falling into the sun, the thruster firing in red, and then a delayed thruster firing for the second one showing in the black line here, such that it achieves its operational orbit about, I think it's about a 2 to 300 day delay, but it's essentially 180 degrees out of phase with the other one. So now you are going over the North Pole with one while you're going over the South Pole with the other. So it takes a little longer to get into that configuration, a total of about 6 years to achieve that, 6.5 maybe, to achieve that operational configuration. But that's a fairly easy way to achieve that phasing. Now, you ask, well, what happens if you can't launch 2 of these very large spacecraft on one rocket? Then, for instance, if you have to use the Falcon Heavy, you can only launch 1 spacecraft at a time. Then, this is an instance where you could launch 1 on a Falcon Heavy, wait on that pork chop plot until the next Jupiter encounter comes by again, 400 days later, launch again, and now you've got 2 spacecraft phased 180 degrees in high inclination orbits, but also phased in longitude on the sun by about 30 degrees. So it's an attractive solution, but you do have to wait for 400 days between launches, and so your final configuration is delayed by over a year because of the launch requirements. And it requires 2 launches instead of 1. It's expensive in that sense, but the attraction here again is that you're seeing more of the sun at once because of the longitudinal separation of the orbit planes, which I think is a nice solution. So in summary, we have a few launch options, right? We've got one in which we simultaneously launch 2 Falcon Heavies, essentially right at the same time, and you achieve the Jupiter transfers roughly at the same time, and you get your configuration set up within that 6-year period, 6.5-year period. The advantages here, of course, are the lower mass per launch vehicle. It turns out you can do, if you do 1 spacecraft for Falcon Heavy, you can even afford to retrieve the boosters, which is kind of nice. It's kind of what the whole point of the Falcon was, you retrieve it. We still have to throw the core away. Unfortunately, there's just not enough fuel for that, but booster return is a nice thing. There's lower risk of a single launch vehicle failure, taking out both spacecraft, of course, if you're on different launchers. The dual spacecraft are operational within 6 years, roughly, again. So that's the disadvantage, of course, is you have 2 Falcon Heavy launches to get your mission up. Various costs of Falcon Heavies, but I don't think they're that cheap yet. Option 2 would be to wait for the SLS Block 1. With the Artemis push, people are saying the SLS is going to actually be a real rocket. That's good news. We could essentially use that to launch both on one launcher. So the advantage is there. You have a single launch. You again achieve your operational orbit and configuration relatively quickly. The disadvantage is that if anything goes wrong, you've lost the entire mission. Both spacecraft go. Option 3, as I mentioned, is you wait 400 days between launches on a Falcon Heavy, and you get your configuration sort of 400 days later than you would if you had a single launch. You still have the high cost of 2 launches, but you also get an added advantage here is that because the launch is delayed by 400 days, you have less, maybe it allows you a little spacecraft schedule margin. So that's about all I have. I just wanted to end on the SLS and how really, really large this vehicle is. I don't think people have appreciated this yet. Shown on the left is the Block 1, which will be flying apparently next year, or 2021 rather. The Block 2 is even larger. And here are the characteristic energy, or C3 capabilities of this rocket in terms of C3 and mass. The mass here is in metric tons. And so you can see for a C3 of 130, which we require, the Block 2, if it's a reality. The Block 1 is pretty much, people are saying, is going to be a reality. That can take about 2 to 3 metric tons out to C3 of 130. The Block 2, however, is 5 to 6 metric tons out to Jupiter. So this is an incredibly large rocket, and it'd be really cool to launch on one of those, I think. So let's hope that actually becomes a reality, but if it doesn't, we can just use either the Block 1 or the Falcon. So that's all I have. I'll take questions or comments on this concept. I know it's kind of again, the concept here was not, oh, let's work within lots of constraints and see what we can squeeze into an existing program. It was to say, what's the science we really want to do in solar physics? And if it's a big mission that's required to do that, let's plan out what that big mission is going to be and not worry so much about existing programs or existing cost constraints. We know we need to see the poles. What is it going to take to do it in the way that we really want to do it? And that's led to this mission concept. So again, thank you.
So you'll presumably be putting this forward for the next Geophysics Decadal Survey, I'm guessing. And,
If it's not approved by then, I mean, come on, let's be optimistic.
and so who is funding? Is it like the spacecraft development cost analysis, the company that hopes to get the contracts, and how that works?
Well, right now, this is all internally funded using CU Trek money, and then Ball is just doing.
Ball is doing it because they're both there.
They're interested in the study. As you saw, they have a heliophysics division now, and this is one of their sort of pie-in-the-sky missions that they're interested in scoping out. That said, they're not getting into detailed design or anything, but I think it's better than order of magnitude estimates on.
So no NASA money per se?
Not yet, no.
Not yet.
No, I'd be interested to hear of potential study money opportunities like that, but I don't know of any personally.
Ways of the capability of SLS left out a comparison of the launch cost.
Is that even known yet?
Yeah, it's around $1 billion.
Yeah.
That's a lot more than one. I mean, it's a lot more than 2.
Perhaps. Do we know the cost of a Falcon Heavy launch? The real cost of a Falcon Heavy launch?
No, it's 100.
Is this weak the recovery option? Because if I understood it correct, they can become the Falcon Heavy for that orbit.
It's a little more expensive, but
Yeah. Yeah, I mean, launch costs are an interesting thing. They're not always as transparent as you think they might be. I was involved in the Falcon 9 launch of Discover, and I can tell you that didn't cost the nominal $50 million that they were saying those launches cost. That there's a lot of things that go into launch costs. But I agree. I mean, the SLS is not going to be cheap. But the point is, if you want to do one launch and achieve this mission in one launch, that is the vehicle that will do it. And again, we weren't concerned about vehicle cost in this study, or cost of any kind, really. It's really, again, what science do we need to do? What's the ideal mission to achieve the ideal science, and operational efficacy as well. I think that's another unique, very unique aspect of this mission. It's not just one spacecraft flinging over the poles once and taking some data and saying, there you go. It's staying out there in perpetuity in a roughly a low eccentricity orbit.
So to go with this operational aspect, I assume you're wanting like 24-hour coverage. So are you limited?
Comms,
telemetry limited?
Yeah, comms are not quite. We haven't discussed those in detail yet. We haven't designed those in detail. You will be eclipsed by the sun at times when you're going around the other side, for instance. Now you're in an orbit like when Stereo was on the backside of the sun. There was a period of time when they couldn't communicate. Now you're doing that every orbit practically. So we do have to work that out. How continuous the data can be is something we're going to be looking into. But I don't think it's
What would data volume, apart from setting aside the continuity of data, can you get all the volume of data down that you want?
Yeah, I think with Ka band we can, compression on board, and also, you're not going to get it right away. It's going to be stored on board, and much like Solar Orbiter is having to do to take the data and then bring it down. Again, we have to do these studies to see just how much bandwidth we're going to have and what sort of eclipse periods we're going to have to work around to get these data down. I think, though, that one of the things we can count on, like Stereo and like ACE, for instance, beacon data of the coronagraph data, very low resolution, but high enough resolution to make the measurements for CME speeds and arrival times will be possible. And that I think we can say that you will get the CME images down on a continuous basis from one or the other spacecraft.
Have you considered using lasers for your interest?
Yes, we have. And every time we talk to somebody about that, they go, "Oh my God, you're going to the sun. We can't talk to you," because of course the difficulty is you've got a lot of background there. I don't think it's impossible, but it's so far been considered, even given how fantastical a lot of the other elements of this mission are, that's the most fantastical, and people are saying that's something that'll have to wait. But I think that'd be fantastic if it did work to use optical. The bandwidth there is so large. Yeah.
So Tom, you're telling us that this mission will require 6 years, roughly 6 years, to establish an operational orbit. Earlier, you mentioned solar sails, which would take a horrible 6 years to establish an operational orbit.
Well,
so what's the downside of the solar sails?
Well, they'll take 6 years to get out of the ecliptic. So they're after launch. It's 6 years before you even get out of the ecliptic. We're out of the ecliptic within a year. We're over the pole within, I forget, 2 years, 2.5 years. So we're looking at the pole directly down in 2.5 years. And now to get into the low eccentricity orbit, which will allow the helioseismology for the next 10 years, that takes 6 years.
So does a solar sail also require a Jupiter encounter?
No, they're doing Venus encounters, so they've got a very low C3 requirement on launch. But I mean, it's interesting to consider that. I don't think it's a bad idea, but it is something that would take a long time. And of course, solar sails of the requisite size don't exist yet. That's another major issue there. The technology we're showing here, none of it is, except for perhaps the laser comm, is unattainable. It's all doable right now. So.
Thanks.
All right, thank you.